So can you see the screen? Please confirm once whether you can see the screen and also audible, right? So in the previous lecture, we discussed about the electronic effects, right? So I had given one question, and that's the orientation of reaction on a aromatic compound, right? So some people submitted the assignment, and only two people predicted correct answer, but they also did not give the exact reason why this is happening. So before starting our today's lecture, I will clarify that. Okay. So our example was so this was our molecule. Here we had CHF2 group, and on that we have given NO2 plus, some electrophile. It may be NO2 plus or anything. And most of the students, they predicted that the reaction will occur at the meta position. And so how many of you still think that it will occur at the meta position? How many of you still think that it will occur at the meta position? Do you think it will occur at the meta position or ortho or para? What do you think? So let me simplify this. Let's say you have given with this CF3. So then what will be the position of electrophilic? Yeah, board is not visible. Yeah, sorry. So yeah, so tell me, for this compound, what should be the position of electrophilic addition, electrophilic substitution? This is very simple. Meta, right? So there is no doubt that in this particular case, electrophilic substitution will take place at the meta position. But what about this one? When one of the fluorine is substituted by hydrogen, what about this? Can you tell? So on which factors the position of attack depends? Yes. Yes. I think your internet. Okay, I got what you want to say, that when electron donation is taking place on the from the benzene ring to the CF sigma star, then you will have positive polarization on ortho and para position, right? So that's what you want to say, right? Okay, that is true. Yes, you are correct. So you are correct that when this in pi sigma star electron donation takes place, a positive charge will come at this three position, and that's why attack from there is not favorable. It's completely correct. But what is the actual difference between this one and this one? What is the actual difference? The difference is the presence of this hydrogen, right? So what this hydrogen will do, what difference it will make in the reactivity? Okay, so this is something to do with the hyperconjugation. One thing you should always remember is that for electrophilic addition, or sorry, electrophilic substitution on aromatic system or nucleophilic substitution on aromatic system, the orientation of the electrophile or nucleophile depends on the mesomeric effect of the group. Okay, so orientation depends on the mesomeric effect, and the rate of reaction depends on the inductive effect. When mesomeric effect is totally absent, then both will be decided by inductive effect. But if for a group both effects are present, mesomeric and inductive, then uh, the orientation will be decided by the mesomeric effect, and the reactivity will be decided by the inductive effect. Now, these, if you consider this CF3 group or this CHF2 group, both are minus I effect group, both shows minus I effect, both withdraws electron through inductive effect. But because of the presence of this hydrogen here, what it will do, it will exert hyperconjugation. So you just leave this fluorine, but this hydrogen, presence of this CH bond, it will create hyperconjugation. So that means hyperconjugation will produce negative charge on the ortho and para position, right? Because if you push the arrow, you will see that positive charge will negative charge will pop up on ortho and para position. So compared to meta, ortho and para position here will be more reactive because of the hyperconjugation. Now, if you consider para and ortho, because ortho position is close to this group, and inductive effect, we know it depends on the distance, right? So because it is close to this group, here the amount of negative charge will be much lower compared to the para position, right? So the attack will take place from the para position. You can tell it in another way also, that is, when attack takes place from the para position, what will happen? So if attack takes place from the para position, like this, NO2H, so then you can see the positive charge will come here, CF2H. Now this positive charge can be stabilized by this hyperconjugating effect. Similarly, if the attack takes place on the ortho position, also the same thing can happen. But when the attack takes place on the meta position, so if the attack takes place on the meta position, you will see that the positive charge will either come here or it will come in other way, that is, it can also come here. In both cases, there is no direct effect of this hyperconjugation on these positive centers. Only what it can do, only this group can destabilize the system by inductive effect. There is no stabilization by hyperconjugation. So for the meta attack, only destabilizing factor is present, no stabilization is present. But for ortho and para attack, both stabilizing factor and destabilizing factor is present. So we have to go with the stabilizing factor. And for the para position, because inductive effect is less felt by the position which is far away from the group, so the attack will take place at the para position. I hope I cleared your doubt. Everyone understood? Do you have any question? Oh, okay. So this is a very interesting question, that's why I gave it. And one two people predicted correct answer, but they didn't mention this hyperconjugation. Whenever you have CH bond and you have to predict reactivity or stability, anything, just think about hyperconjugation once, because hyperconjugation plays important with, although it is a in terms of magnitude it is a very small effect, but when when question comes of deciding the reactivity, it is very important. Okay, now let us go to our uh, let us go to our today's topic. So acid base we will discuss today, and these are the topics which we will discuss. So here is the list of topics. I am not reading out it again because that will just take time. So first, what we have to know about acidity and basicity is the pK. Okay, let me see how many students are there. Okay, so 46. Yeah. Okay. So first we have to know about the pK. Okay. So whenever I am not audible or you cannot see, just inform me. So pK, I am not going into the derivation of pK, all these things, because as organic chemist we want the qualitative picture of pK. We don't need the derivation and all these things. So qualitatively, what pK means, we know pH means the concentration. So it is actually minus log of H plus, right? Minus log of H plus, and actually pH means what? pH means the dependence. So pH actually depend on the concentration of H plus ion in a solution, right? If the H plus ion concentration is higher, pH will be lower, and vice versa. Similarly, we can say for pK also that for a weak electrolyte, for a weak acid, we can say for a weak acid, if the pK is higher, that means acidity will be lower. Similarly, if pK is lower, that means acidity will be higher. So for pK you just have to remember this thing. You don't need to remember any derivation or anything, especially for organic chemistry. For physical chemistry you have to derive the things and all that, but for organic chemistry, if you just remember this relation with the acidity and pK, that is enough. So pK higher means acidity will be lower, yeah, and pK lower means acidity will be higher. So let's say you have given two pK values. For compound 1 the pK is -2, and for compound B the pK is 4. So which one is more acidic? Can you tell which one is more acidic? Yeah, so that's the simple thing. You have to just remember that if pK is lower, the acidity will be higher, and nothing more. Okay, so now we'll go into the factors which decide the acidity. Okay, so before that, I want to say that see, there is just one thing you have to remember, that acid means which gives H plus, base means which accept which gives electron, right? So I am not going into the definition of all these things because these are very preliminary topics and we are talking about csir-net. So we will discuss more examples here. So I have a lot of examples we will see shortly, but here I just want to say acidity means the uh, the species which gives H plus is acid, as simple as that. Now what are the factors on which the acidity depends on? This is very important. So there are four important factors on which the acidity of a molecule or a acid depends on. So if we have a acid AH, then first factor on which the acidity will depend on is the strength of the AH bond. Okay, the strength of AH bond. So I'll show you this by one example. So whenever you have to predict or you have to compare the acidity of two or more molecules, you have to first look into the bond strength. Let's say you have given with HCl HBr and HI. So first tell me, if you have given this HCl, HBr and HI in a aqueous solution, what will be their acidity order? Can you predict? Anyone? So everyone agree with that, or do you have a different opinion? Hmm. Okay, so we got one answer that HCl is greater than HBr than HI in aqueous solution. Anyone? Anyone want to say? Okay, okay, that's okay. So everyone agree with that, or do you have a different opinion? So do you know about leveling effect? Leveling effect of solvent. Have you ever heard about that leveling effect? What is that? Can you tell what is leveling effect of a solvent? Anyone? Okay, fine. If you don't know, that's completely fine. So one of the factor on which the acidity depends on is the solvent, and acidity of a molecule can be different in different solvents. For example, if you consider ammonia, we know ammonia is a base, right? So when we consider ammonia in water, then ammonia is basic. But if you take a more basic solution than ammonia, then ammonia will not act as base, right? So acidity or basicity, this is a relative thing, and it depends on the solvent. Which solvent we are talking about? So here we are talking about aqueous solvent. And what is leveling effect? Leveling effect is, so let's say you have given with three acids A, B, and C, and for a particular solvent, let's say S1. In S1 solvent, A is more acidic than B, which is more acidic than C. In S2 solvent also the same trend is followed. Likewise, you just vary solvent from S1, S2, S3, S4 like that. Now you reach a solvent S5 where all A, B, and C behaves equally. Their acidity becomes same. Irrespective of their chemical nature, they behave same, their acidity becomes same. So this S5 is called the leveling solvent for these three acids. So leveling solvent is such a solvent where all the acids what we are comparing, they will behave same way. Now how this can be? So if you remember, all these HCl, HBr and HI, they are strong electrolyte, right? They are strong electrolyte, and in aqueous solution they dissociates completely. So if you take 100 moles of HCl, you will get 100 moles of H plus and 100 moles of Cl minus. Similarly, if you take 100 moles of HBr, you will get 100 moles of H plus, 100 moles of Cl minus. Same is for HI. So in aqueous solution or in aqueous solvent, all these molecules, HCl, HBr or HI, they will completely dissociate, right? There will be no difference. If you take them in organic solvent or in like um anhydrous medium or vapor phase, then their acidity will differ, because then they will not dissociate completely. But in aqueous solution, they will be completely dissociated and their acidity will be same. HCl, HBr, and HI will not have any difference in their acidity. Do you understand this? So in aqueous solution, if you take a strong acid, there will be no difference in acidity. If you take HCl, HBr, H2SO4, HNO3, whatever you take, if it is a strong electrolyte, their acidity will be same. And because water is leveling solvent for them, in any leveling solvent, if you take different acids, and if the solvent is leveling solvent for these acids, then their acidity will not be different, their acidity will be same. When we take this HCl, HBr and HI in a solvent which is not a leveling solvent, for example, if we take them in a organic solvent, then their acidity will differ, and now their acidity will be decided by the bond strength, the HCl, HBr and HI bond strength. Now if you go from HCl to HBr to HI, as we go from Cl to Br to iodine, so you just answered this, that's that the size of the halogen atom increases from chlorine, bromine to iodine, and we can also include here the HF. From fluorine to chlorine to bromine to iodine, size gradually increases, and as a result, the overlap with hydrogen 1s orbital gradually decreases, right? So combining these two factors, the bond strength will be highest for HF, then for HCl it will be lower, for HBr it will be even lower, and for HI the bond strength is very less. So HI can dissociate very easily to H plus and I minus. So whenever you are taking a solvent which is not a leveling solvent for this, then HI will be dissociated maximum, then HBr, then HCl, and then HF. So that's why the acidity strength will be, HI will be most acidic, then HBr, then HCl, and then HF. Do you understand this? So this is the first thing on which the acidity of a acid depends on, the bond strength. Now, what is the second point? So now let's say you have to compare two things. One is, let's say you have ethanol, acidity of ethanol, and um, acidity of let's say uh, sorry for this inconvenience. I don't know why this pop-up is coming. Okay, so if you have to compare between ethanol and let's say, um, so first point we discussed about is the strength of the bond, AH bond. The next thing will be, so let's say you have to compare between ethanol and ethane, CH3 CH2H. So can you tell which hydrogen will be more acidic, the hydrogen here or the hydrogen here? Which hydrogen will, why? Why, if you consider the yeah. So it is clear that the second point on which the acidity will be dependent on is the electronegativity of the atom A. So first we have to look into the bond strength, or this will be so first we have to look into the bond strength, and then we have to look into the into the electronegativity of A, because if you consider OH bond and CH bond, the bond strength will differ very slightly. Okay, because both oxygen and carbon are in the same row in the periodic table, or also in the sorry, not same row, but they are in the same row in the periodic table, and their size is comparable. So the OH bond and CH bond will not differ much. Okay, and that's why in this case the bond strength cannot decide the acidity. You have to go into the electronegativity of the two atoms, the oxygen and the carbon. The third point on which, so the second point is the electronegativity of A. What is the third point? So let's say now you have given with uh, ethanol and acetic acid, CH3COOH, acetic acid. So can you tell which one will be more acidic between ethanol and acetic acid? Why? Why acetic acid? Because in this case both are oxygen, right? Both A, we can say oxygen. So electronegativity is also same, bond strength is also same. So what is the deciding factor here? Yeah. So that means here yeah, tell. Yes. Yes. So the point here is the stability of conjugate base, right? So when both factors are same, the bond strength is same, the electronegativity is same, then we have to look into the stability of the conjugate base. For ethanol, the conjugate base is like this, ETO minus, whereas for acetic acid, the conjugate base is this one, and it has two equivalent resonating structures, right? So these are the three main factors on which the acidity of a molecule depends on. Now the fourth factor is the solvent effect, and because here whatever we will talk, we will compare the acidity of different acids in same solvent. So we can take it as constant, but if we vary the solvent, and we have seen at the start of this lecture that as we vary the solvent, the acidity can also differ. So the main 3 points are the strength of H bond, the electronegativity of A, and the stability of the conjugate as conjugate base, that is A minus, right? So these are the three factors, and the fourth factor is the solvent. So if you just understand these three principles, you can get complete idea of acidity and basicity. For this course will be very easy for you. So I hope that till now you don't have any doubt. If you have any doubt, you can ask me. So can I proceed further? Okay. So now we will talk about the acidity of aliphatic carboxylic acid, but I will talk a very little bit about that, because we can talk a lot about this simple aliphatic carboxylic acids. That will just take more time and nothing, because you can read any books, and what I will suggest for this is Peter Sykes. So Peter Sykes, you have a chapter of acid base which is very small chapter, like 10 pages, so you can easily read that. So here you will have a lot of examples, you can read from there. You can also follow Jerry Merch. A lot of examples are there, but I will talk about a few examples of aliphatic carboxylic acids, and then I will go into the more relevant examples which will come in your exams. Okay. So if we talk about aliphatic carboxylic acid, it means simple carboxylic acids. And what to say? So simple carboxylic acid has this group, carboxylate group, and here you have this alkyl chain. Now anyone can tell that if we put more alkyl substituent here, let's say you compare with simple acetic acid, and when we substitute this methyl group by two more alkyl groups, so if this is A and this is B, what will be the acidity order? It's very easy, right? You can tell. Yeah, because of the inductive effect present in the B. So inductive effect will destabilize the conjugate base, right? Similarly, if you compare this one with a substituted acid where the substitution is the halogen substitution, let's say you put three fluorine atoms over here. So now, let's say this is C. So what will be the acidity order A and C? Can you tell? C is greater, because here the conjugate base is stabilized by the minus I effect, right? So this is very simple. If you put a electron donating group, it will decrease the acidity. If you put electron withdrawing group, it will increase the acidity, right? So this is about the aliphatic carboxylic acid. You can, if you want to learn about more examples, you can read Peter Sykes. A lot of examples are there. I am not discussing that here. So now aromatic carboxylic acid. Now aromatic carboxylic acids are of two type. One is aromatic acids are of two type. One is carboxylic acids, aromatic carboxylic acids, and another one is phenol. So phenol is also acidic. Phenol is also acidic, unlike aliphatic alcohol. Aliphatic alcohols are not acidic, but aromatic alcohol, which we call phenol, they are acidic. So first tell me why phenol is acidic and aliphatic alcohols are not acidic. Can you tell? Yes. So you are trying to say that in case of phenol, when it gives a proton, we have a conjugate base like this, right? We have a conjugate base like this, and this conjugate base is actually stabilizing, or it is in resonance with the aromatic ring, right? Now my question is, if you see in the phenol itself, you have this lone pair, right? And this lone pair can also come into resonance with the aromatic ring. So whatever point I discussed here, the stability of the conjugate base, there is a hidden thing which I did not talk. That is the stability. What we are talking about is the stability with respect to the undissociated acid. So we are talking about the stability of conjugate base with respect to the stability of our undissociated acid H. We are not talking about the absolute stability of the conjugate base. Okay, so if we put in energy profile diagram, if we put it in an energy profile diagram, let's say here we have the energy of our undissociated acid, and here the energy of our conjugate base. So if the energy of conjugate base is lower compared to undissociated acid, then only it will show acidity. If the stability of the conjugate base, let's say absolute stability of the conjugate base is very high, but your undissociated acid is even more stable, then it will not show acidity. So here the thing you have to remember, that in the ground state also this resonance is there. So what is the need of this phenol ring to lose a proton and then go into the resonance? Can you tell? Because it can enjoy the resonance in the undissociated form also. So what is the need of this undissociated phenol to go into the phenoxide and then come into the resonance? Can you explain this? Try it. Anyone want to try? So where, for the conjugate base or for the undissociated acid? Yes. So there is one point. So what is your name? Akash. Okay. So Akash is saying that when this resonance is happening in the ground state, then positive charge is coming on electronegative oxygen atom, right? So this is one thing, that you are putting positive charge on electronegative oxygen atom. So rule of resonance says that we when we put positive charge on electronegative atom, that is a destabilizing situation. So this is one point. Another point is that charge separation is always a bad choice than than a neutral case. Okay, so this is a neutral molecule, and forcefully here you are separating a charge. And Coulomb's law, what it says that when you put two unlike charges, one positive and one negative charges, they will attract one another, and as you pull them apart, the potential energy of the system goes up, right? So here you are forcefully separating positive and negative charge, and you are pulling them apart. One is this corner, another one is this corner. So that means here the destabilization increases. But in this case, you are spreading a positive negative charge. Here you have a residual charge. You are not separating a charge, rather you are delocalizing a residual charge throughout the molecule, right? So throughout the molecule, your negative charge will come here, it will come here, and it will come here. Okay, so instead of placing the negative charge only on one center, you are just delocalizing the charge, the negative charge, all over the molecule, and that's why it is a more stabilizing situation compared to the ground state. And this is the reason why phenol is acidic. Understand? So from here we understood the one principle, that charge separation is not a good choice, but delocalization of charge or spreading of charge is a good choice. So that is our take home message from this particular thing. Now two things are there. So one is carboxylic acids, the aromatic carboxylic acid, and another one is phenol, and we will see the acidity of these two. So now if you are given with two molecules, like let's say you have this COOH over here, and in one case you have a nitro substituent at the meta position, and in another case you have a nitro substituent at the ortho position. So which one will be more acidic? And yes, tell. And for para, so if you compare between meta and para, which one will be more acidic? Para will be more acidic. But you are saying para is more acidic because you are thinking that the negative charge which will be created in the conjugate base will be delocalized in the nitro group, right? That's what. Hmm. Yeah. Yes, that cannot enter into the ring, right? Yes. Okay. Hmm. But yes, but when nitro group, when we are talking about the electron withdrawal by nitro group through its minus R effect from the aromatic ring, it does not depend on the position of the nitro group, right? Because uh, wherever it is, it can pull same amount of electron from the ring. Is it not? So, so if you hmm, hmm, mm, hydrogen bonding. So you are talking about this. You are talking. So here, hydrogen bonding. I don't think hydrogen bonding happens when NH2 group is present. Then hydrogen bonding occurs. With nitro group, hydrogen bonding is there. So 1, 2, 3, 4, 5, 6, 7. 7-membered ring. When it is in negative charge, it is in like this minus. How hydrogen bond? Yeah, but you if you count, this is 1, 2, 3, 4, 5, 5, 6, 7. So 7-membered ring will form, right? It is not a stabilizing situation. So hydrogen bonding occurs when we have NH2 group, not NO2 group. Okay. So here the main thing is you just said the right thing. So when nitro group is present in the ortho or para position, then uh, positive charge will come at this ipso position, right? If you try the resonating forms, there will be a positive charge on the ipso position, but for the sorry, for the ortho and para, but for the meta, the positive charge will comes here, here, and here, not at the ipso position, right? Now when it is in the conjugate acid form like this, so if your positive charge is at the ipso position, that is a more stabilizing situation compared to when positive charge is on these positions, right? So that's why this ortho will be most acidic, then para, and then meta. Actually the difference between meta and para is very less. So here the distance factor, the inductive effect, and this ipso position positive charge, they actually compete with one another, and that's why their acidity difference is very less. But one thing is for sure is that ortho will be most acid, right? Yeah. So that's the thing. Now if you put more nitro groups, the acidity will even increase. Similarly for the phenol, if you put nitro, now in phenol it is interesting. If you put nitro group at the meta position, the acidity increase is not that much, because here you have a possibility of delocalization of the negative charge on oxygen atom inside the ring, right? And when it is at the meta position, the delocalization is not possible, but when the nitro group is at ortho or para position, then delocalization can be possible. So for phenol, if you put nitro group at the ortho or para position, then your acidity will, yeah, tell. Yeah, ortho effect is also there. So here you have hydrogen bonding, right? Because here you will have a 6-membered ring, right? So this is the reason why ortho will be less acidic than para, because when we dissociate the acid, the hydrogen bonding will break. So in the undissociated form, you have this hydrogen bonding, right? You have this hydrogen bonding which will break when it will dissociate, right? So that's why the ortho will be less acidic compared to para. Yeah, that's completely right. So that's pretty much about the aliphatic aromatic carboxylic acid. Now we will look into some more interesting examples. Okay, so first one is this one which we just discussed, that effect of the hydrogen bonding, this one versus this one, and you have seen that para is more acidic than ortho, right? Now can you tell what will be the acidity order of these three? Let's say this is A, this is B, this is C. Can you tell the acidity order? This is one of the interesting example. So here it is this one, acidity order. Can you tell acidity order for this A, B, and C? B B is most acidic. B is most acidic. Then C, then A. So everyone agree with that? You are saying B is least acidic, then A, then C. So can you tell the reason why you think so? So first tell me why C is most acidic. First tell me that. Hmm. Yeah. Hmm. Hmm. Okay, so what? So everyone agrees with that? Everyone agrees with that? Or do you have some other answer? So here one point you are missing. Okay. Yes. So you have to consider the hydrogen bonding also. So that point you are missing. So you can see for molecule A, the hydrogen bonding is present in the undissociated structure like this. So there is one hydrogen bonding. Sorry, this is H. Yeah. So this is the hydrogen bonding, right? So now I have given you a clue. Now can you tell what will be the order? So first tell me what will be the most acidic. A, B, and C. What will be the most acidic? A is most acidic. Why? Why? So when it goes to the conjugate base form, it will be CO minus, right? You are saying it will be CO minus, and then hydrogen bond will be even more stronger. Yeah, this is completely correct. A is most acidic. Then between B and C. So in B and C, hydrogen bonding is absent. So we don't have to consider hydrogen bonding. Now tell. Now, whatever you were just telling that the negative charge on ipso position, you try to say that, right? So yeah. So then C, then B. The reason is very clear because in case of B, oxygen will push electron and negative charge will come at the ipso position. But in case of C, the situation is not there, right? So this is the order. Okay. So this is a very important example. It can come in exam. Now another very important and one of my favorite example is this third one. So this is, let's say P, this is Q, this is R. Can you tell the acidity order? So here R is most acidic, then then Q and P is least. So yeah, you predicted correct, but can you tell why? What is the reason? Why is this order followed? What is the reason? I think you are not audible properly. Yeah, can anyone tell why this order will be followed? Can you just elaborate what planarity factor you're talking about? Someone is trying to say something. Please. Please tell. Okay, so let me tell you. So in all the cases, these are the acidic hydrogens, right? Now, if you just draw the conjugate bases in each case, so in first case, the conjugate base will be this one, negative charge, these two aromatic rings. In second case, it will be this one. In second case, it will be this one, and also this ring is there. So you have this negative charge over here, and in third case, you have this. Third case. In third case, you have this negative charge over here. Okay. Now, one thing I said previously, that when you are talking about the stability of the conjugate base, you have to compare the stability of the conjugate base with its undissociated form. You don't have to compare between this conjugate base, and this conjugate base. You don't have to compare between these three. Rather, you have to compare between R and its conjugate base, let's say RCB. Q and its conjugate base, let's say QCB, and P and its conjugate base, let's say PCB. Okay. Now, if you see P, in case of P, these two rings are already in conjugation to one another, because the molecule is planar. The molecule is planar, and in the ground state also, they are in conjugation with one another, right? So only extra stability gained when it goes to its conjugate base form is that another aromatic ring come into the picture, and now the whole system is in conjugation, and the whole system is now uh, whole system becomes aromatic, right? So there the gain of stability is not that much, because it was already the two rings were in conjugation. For molecule key, if you consider the molecule key Q and its conjugate base QCB, then you will see that here also these two rings are in conjugation. Only this ring is not in conjugation, because you have a saturated center in between. But when it goes into the into the conjugate base form, then one new aromatic ring come into the picture. At the same time, this other ring come into resonance with all the three rings. So now the whole system becomes planar. And here, if you compare the stability gained from P to PCB, the stability gained by going from Q to QCB is much higher, because one extra ring come into conjugation. And for R, you can see the system is such that in the ground state, all these three rings are in a non-planar way. They are not in conjugation with anyone. But when it goes into the conjugate base form, all comes into planar in same plane with one another. So now all these three rings, as well as these new two aromatic rings, they are in the same plane, right? And that means the stability gained from going from R to RCB is the highest. So whenever we are comparing acidity or basicity, we have to compare one acid with its conjugate base, not among all the conjugate bases. So the stability gained for R is highest, then for Q, and then for P, and that's why R will be most acidic, then Q, and then P. Hope you understand. Yes, yes, yes. Yeah, for q you can see these two rings are in the same plane, right? So they are in conjugation in the ground state also. But this ring is not in conjugation with them because here you have a sp3 center, right? But when it goes to the conjugate base form, this center becomes sp2, and all the three rings now come into conjugation with one another. So that's why the stability gained here is higher compared to P, because in P, two rings were there which are in conjugation with one another in the ground state. In the conjugate base form also two rings are there in the conjugation. There is no extra ring, right? So this is the reason why R is most acidic, then Q, then P. Understood? Okay. So now, what about dicarboxylic acid? So if you talk about simple dicarboxylic acids, if you talk about this acid, let's say COOH and CH2 COOH. This is, what is the name of this acid? What? Yeah, malic acid. Malonic or malic? Yeah, malic acid. So there is a mnemonic, Ohm's cap, oxalic acid, malonic acid, succinic acid, then glutaric acid and palmitic acid. There is a name as we go from carbon number 1 to 3, the name goes. So can you tell, if you consider the acidity of this, let's say CH3 COOH and this one, so this is A, this is B, which one is more acidic? A and B, which one is more acidic? Acetic acid and malic acid. B is more acidic. Why? Let's see, hydrogen bonding is there or not. So you have this OH and you have this. Oh, yeah, so hydrogen bonding is present. Yeah. So one factor is hydrogen bonding, and second factor is the minus I effect of this group, right? Minus I effect is also present. So now let's say we compare the acidity. So this will have two pK values, right? Because it has two acidic group, it will have two pK values. So this is, we are talking about pK1 of this, and this has only one pK value. So pK of this and pK1 of this. What about second pK? So if we consider pK2 of this acid and acidity of this A, then which one will be more acidic? Can you repeat once? Why? Yeah, so one reason hydrogen bonding will be destroyed at the and at the same time, if you see, yes, minus I effect is also there. Sorry, here you will have plus I effect, not minus I, plus I effect. So if you just remember the first class, I have said that when carboxylic acid in the carboxylic acid form, it will show minus I effect, but when it becomes carboxylate, then it will show plus I effect, right? I told that in the first lecture. Similarly, for case of oxygen, if it is in OH form, it will show minus I effect, but when it is in oxide form, it will show plus I effect. So now in the first case, it is showing minus I effect, but when we are talking about second pK value, pK2, then it will exert plus I effect, and that will even destabilize the conjugate base, right? Now, can you tell the name of these two, this A and B? Yes, this is the maleic acid. And what about the comparison of pK1 of these two? For which one the pK1 will be higher? For A, pK1 will be higher. Why? So which one will be more acidic? Yeah. So you said A. but it is B. B is more acidic, right? Because yes, when it goes in the conjugate, so in ground state also hydrogen bonding is there, but when it goes into the conjugate base form, the hydrogen bonding is even more stronger, right? So B is so for comparison of pK1, B is more acidic than A. But what about pK2? What about pK2? Why? Yes. So one reason is hydrogen bonding is destroyed when we consider second pK, and the second reason is yes, still. So I'm giving you a clue. This one is uh, no, plus I effect is present in both case, right? In both case, plus I effect is present. Steric or Coulombic? Yeah, dipolar repulsion or Coulombic repulsion, because for fumaric acid, you can see these two are trans with respect to one another, so there is no direct Coulombic repulsion. But for the maleic acid, there is severe Coulombic repulsion, right? So this is the reason why uh, for this dicarboxylic acid, the first pK of B is higher, but if you consider second pK, it is higher for A. Okay. Now, so these are the examples of acid. You can look for more examples in many books, but whatever I got, I presented here, and these are most important examples. Later, if I get more examples, I will also discuss with you. Now, let us talk about bases. So, for bases, we can express the strength of base with pKb or with pKa also, but when we talk about pKb, it is the pKb of the base. For example, if we talk about pKb of NH3, that means it is pKb for NH3. But when we talk about pK of NH3, what we are actually talk about? What we actually talk about? So let's say we say not NH3, but let's say we have some NR3, and we say that its pK value is, let's say, 6. I am just quoting some arbitrary number. I don't remember the exact value, but let's say we say that pKa of NH3 is 6. So what actually this refers to? What exactly it tells? Can you tell? Not NHR3, but NR3H plus. NR3H plus. Yes. So yes, after taking proton, the conjugate acid is formed, and when we talk about pK of some base, we actually talk about pK of the conjugate acid of that base, right? So here we talk about the pK of NHR3 and this is H plus. So we talk about pK of this. So this is so for pK of base, you just know about this. You don't need to know anything else. So here we can say that if pK of a base is higher, that means basicity will be higher or lower. pK higher means basicity will be pK higher means basicity will be higher, and pK lower means basicity will be lower. So here the relationship is proportion, right? Now again, for aliphatic bases, what are the aliphatic bases? Generally the amines are the aliphatic bases. Amines are considered as the aliphatic bases. Okay. And for amines, if we talk, then you will see that as you put R group on the amine, what will be the order? So let's say you have three amines. One is this RNH2, this is A. Another one is R2NH, this is B, and another one is R3N, this is C. So what will be the acidity or sorry, basicity order of these three? Can you tell what will be the basicity order? A is more basic. C is most basic, then B, then A. What is the reason? What is so one answer I got is this one. Another answer I'm getting is B, then then A. Okay. Any other answer? Okay. Now explain. Whoever said A, one is a correct answer, and whoever said two is correct answer. Can you explain why you are saying like that? Yes. Yes. So. Hmm. Hmm. Yes. So everyone understand that? So we have to consider both effects, inductive effect as well as hydrogen bonding. So if we just take inductive effect, then the order should be this one: C greater than B greater than A, because as we put more R groups, the inductive effect increases and nitrogen atoms lone pair donorability increases, right? But we cannot take only inductive effect into account. We have to take the solubility also into consideration, and when we take solubility into consideration, we will see that the tertiary amine, in case of tertiary amine, the conjugate acid whatever will be formed, the solubility is very less for it. Okay, solubility. So if you consider gas phase basicity, then this is the correct answer: gas phase, because there is no solubility, only inherent electronic nature plays the role. But when we talk about basicity in solution, then we have to incorporate the acid solubility factor, and when solubility factor comes, so we have to take inductive effect as well as solubility, and then this will be the order. So B will be most acidic, and actually this is not the order. So C will have least acidity. Okay, C will have least acidity. So uh, B will be most acidic, then A, then C, because for C the solubility is very less. Okay, it is so less that it will be least acidic, least basic. Okay, so B will be most basic, because here is a balance of inductive effect and solubility. For A, the conjugate acid is highly soluble, and for C, although inductive effect is there, but the solubility is very less. Okay, so with aliphatic amines, this much you have to know, nothing more. Okay, now for aromatic bases. Okay, so for aromatic bases, what are the aromatic bases? Aromatic bases are again aromatic amines, which we call aniline, right? Anilines are the aromatic bases. Now for these anilines, we have some interesting things, okay, that we will discuss. So first of all, amine will be not very much. So if you compare aniline and a simple primary amine, which one will be more basic? Which one will be more basic? Why? Why? Can you tell why? Very simple. Yes. Yes, yes. So you are talking about inductive effect, right? So inductive effect is there, but that is low. But main factor here is the delocalization of this lone pair inside the ring, right? So in aromatic amine or aniline, the nitrogen lone pair is, yeah. Please mute your audio. So for aniline, the lone pair is delocalized inside the ring, right? It is delocalized inside the ring, and that's why the nitrogen atom vulnerability decreases. But for aliphatic amine, the vulnerability is high. Now, for the comparison of basicity of any aromatic amine, only one factor, this nitrogen atom lone pair availability, this is the one factor you have to consider in every cases. Okay, so that means, let's say you put some R group over here, some alkyl group. So will the basicity increase or decrease? What will happen? Can you tell what will happen if you put some R group on the para position of the amine? What will happen? Am I audible? Yeah. So you are there. So can you tell, if I put some R group into the ring, what will happen? It's very simple, right? Density will increase or decrease. Yeah, it will definitely increase because R group will push electron. And what will happen if we put nitro group? Yeah. So simple thing. If we put electron donating group, the basicity will increase. If we put electron withdrawing group, the basicity will decrease. Now let us see some important examples, some interesting examples. So first one is this A and B. Can you tell what will be the basicity order? A and B. In both cases, we are putting methyl group into the ring. In one case, we are putting in the ortho position. In another case, in the para position. So, uh, which one will be more basic, A or B? Which one? Why? Why? Whoever telling A and whoever telling B, can you give me the reason? Please give the reason why you are thinking that A is more acidic, or why you are thinking B. Sorry, why you are thinking A is more basic or B is more basic? Hmm? Inductive effect. What is ortho? What is ortho effect? Hmm. But hyperconjugation is present both in ortho and para, right? Ortho and para are same in terms of position. Not exact, not exactly a steric factor. When NH2 is there, a hydrogen is very small, so steric factor is not that much here. So you have to consider the stability, solubility again, right? So if you consider the two cases, this is NH3 plus and this is also NH3 plus. Now when you talk about so in both cases, inductive effect and actually the electron push from this methyl group is almost same for both cases, A and B. You can say for A, it is close to NH2, but you have to think whole system, not the distance. So here the distance is not a main factor, and in both cases we can say the electronic effect, the electron push effect is almost same. But what is different here is the solubility of the conjugate acid. Now when we talk about the solubility of A, when water molecule comes closer to solubilize the system, it will face some steric hindrance from the methyl group. But because here the methyl group is too far away from the positive center and from the center where the solubilization will take place, so here methyl cannot create any steric hindrance. So that means this B conjugate base of a conjugate acid of B will be highly soluble, and solubility is lower for conjugate acid of A. So that's why B is more basic compared to A. Clear? For basicity, solubility factor is very important. Okay. Now, what about this A, B, and C? Can you tell what will be the basicity order? B, A, C. Now, can you tell what is the reason here? Why you think B is most acidic and most basic? Yes. Yes. So you are correct, but in addition to solubility, one extra factor is there. Can you look into the molecule and try to find out what is that? Have you heard about steric inhibition of resonance? So among A, B, and C, where steric inhibition of resonance is present, and A, steric inhibition of resonance is present in both C and A. In C, the degree of that is high, but in A also it is present. Methyl group is there. And here you are not talking about NH2, but you are talking about NH2, right? So in both A and C, steric inhibition of resonance is present. Okay. Now, can you tell what will be the order? C, A, B. So one thing is for sure that A is most. Sorry, you said C, right? So one thing is sure that when steric inhibition of resonance is present, then nitrogen lone pair delocalization is lower and the basicity will be higher, right? So that is for sure. But here in C, whatever nitrogen atoms lone pair vulnerability increases by steric inhibition of resonance, that is actually compensated or overcompensated by the solubility factor. Here the conjugate acid whatever will form, sorry, this N, this methyl hydrogen. So this thing, if you see, there is too much steric clash. There is too much of steric clash in the molecule. Okay. And solubility is highly hampered by the presence of these two methyl groups. So the C is so much uh, insoluble. C is so much insoluble that its basicity is the lowest. So here C will be the least basic, then B and A will be the highly basic. So in case of A, both the steric inhibition of resonance as well as the solubility factor is present. So both are enhancing the basicity. For B, there is no steric inhibition of resonance, but these methyl groups, they are pushing electrons, so nitrogen atom vulnerability increases. That factor is present. For C, although the steric inhibition of resonance is present, but the solubility is very low, and that's why it is least basic. So the basicity order will be this: A will be most basic, then B, and then C. Okay, understand? Okay, so then this is A, this is B, this is C. Can you tell the basicity order of these three? Which one will be most basic? C is most basic. Then what is the reason? Can you explain? Which one is more rigid? Between C and B, which is more rigid? Are you sure? Why you think? Here you have two carbons, right? And here you have only one carbon. So which is more rigid? B is more rigid. Right? So then can you tell again what will be the order? B will be most basic, right? The order will be B, then C, then A. So in case of, so here all the main thing is the directionability or the directional property of the nitrogen lone pair, in which case the directional property or the nitrogen atom is more directed towards the proton. There the basicity will be highest, and as the directionability decreases, it will be low. So, and also one thing you have to compare again. uh, the main thing of acidity or basicity, it is because it is a thermodynamic factor, so we have to compare the stability of conjugate base and undissociated acid, or conjugate acid and the undissociated base, right? So uh, in all the cases, as the base, so nitrogen is there, so as the base goes from the base to the conjugate acid form, so this center becomes tetrahedral. So initially it was also tetrahedral, but one position is occupied by the lone pair. But now it becomes tetrahedral, and the position is occupied by a proton. So there is a change of bond angle, right? There is a change of bond angle. It for this molecule, the bond angle is more tetrahedral bond angle, which is 109.28 degree, right? And here in the initial form, because lone pair is there, so the bond angle is deviated from the ideal tetrahedral bond angle. Now whenever the change in bond angle is higher, that process is less favorable, right? So for the most rigid system, the change in bond angle will be the lowest, and for the most flexible system, the change in bond angle will be the highest, right? Because here this bond angle is not 109 degree at all, but when it will go to the conjugate acid form, it will achieve the tetrahedral bond angle, right? And that's why it is resistance toward taking a proton. Okay, you understand? Hello. So what directional property? So if you draw the lone pair, so here it is directed like this, here also it is directed like this, but here it can be so actual structure of this will be something like this, right? Something like this. Okay, right? So in all cases, the nitrogen atom lone pair has a directional property, but where the rigidity is more, so this thing can flip. It can also flip. Okay, it can flip, and then its directional property will change. So now you can see it changes. So its direction continuously changes. There is a flexibility. As more flexibility is there, the direction of nitrogen lone pair is changes. It goes through a planar form also, right? It goes through a planar form also. Then there is no directional property of the lone pair. But for a rigid system, the direction is always fixed, right? And that means when the direction is fixed, it will take a proton more easily, right? So that's why for a rigid system, the acidity is higher compared, sorry, the basicity is higher compared to a non-rigid system. This is one explanation. Another explanation is that whenever a nitrogen containing base or a amine base is taking a proton and going to the conjugate acid form, you can see it is going to a tetrahedral structure. Initially it was also a tetrahedral structure, but now in the tetrahedral structure, instead of lone pair, you have a real atom, right? And when you have a real atom, the bond angle will be more close towards the ideal tetrahedral angle, which is 109 degree. Now let's say here you have a bond angle of 105 degree, and from there you are going to a bond angle of 109 degree. So there is a change of bond angle of only 4 degree. And now let's say you have a bond angle of 90 degree and you are going to 109 degree. So now you have a change of bond angle of 19 degree, right? So when you are trying to change the bond angle more, the system will resist. It will not like to change its angle, right? So in this case, the bond angle is mostly deviated from 109 degree. But for these two, it is more towards 109 degree. And that's why this A, when you want to change its bond angle by giving it a proton, it will resist more. And that's why its basicity will be lowest. Understand? Okay. So now this one, A, B, and C. Can you tell their basicity order? This is very common example, but also important. So here you only thing you have to consider is the stability of the conjugate acid. Hmm? Which one is more? A. A is most acidic, basic, then B, then C, right? So here, if it takes a proton, it will take proton from where? Here, right? Plus, and you will have three equivalent resonating structure, right? Here you will have two equivalent resonating structures, and here you don't have any resonance at all, right? Do you agree with me? Okay, so most number of resonating structure means most stable. So A is most stable, then B, then C. Okay, now this is question from CSI net exam, last exam, that is December November 2020. So this is A, this is B, this is C. Which one is so what will be the order of basicity? Can you tell? There are two basic centers, but you have to tell the basicity order. You don't have to bother about the two basic centers. What will be the order? C is most basic, then B. So someone is say B is most basic, then C or B, A, C or A. Then A, then C. Okay, so can you explain why you think so? Why B? Hmm. Hmm. Yes. Yes. So one thing is sure that C is least acidic because there is a steric hindrance. Yes. So now between A and B. So you if so in A if you see the nitrogen can exert plus R effect as well as minus I effect, right? Right. But in B the other any NME2 group is far away from the one in Me2 group. So it can exert only plus R effect and no minus I effect, right? So what? Yeah, tell. Hmm. Yeah, that is questionable because only three up to three carbon it is valid, right? But whatever I can say at this moment, no other thing I can say. I mean, there is no other factor. The only factor is because resonance does not depend on distance. Okay, so the resonance effect will be both in case of this one and this one. Only effect here which can make a difference is the inductive effect. But I have some. I'm not saying that I'm sure about it. You can, if you have different opinion, you can tell, and I will check it and I will confirm that. But for now, what I can tell is B will be most basic, then A, and then C, because between A and B, maybe some electron withdrawal is there from this NME2 group. Maybe, I'm telling. I'm not. Yeah, yeah. Tell if you have any opinion. Yeah, yeah. It is a proton sponge, right? We did not consider that. Yeah, it is a proton sponge. So here, what he is telling is when we take this one, the yes, the the hydrogen is highly, uh, I mean highly. There is a hydrogen bonding effect also. I mean this is called proton sponge, right? So that means C is most basic, right? Yeah. So we forgot about that, the proton sponge effect. Yes. Thank you for remembering. So C is actually called. So this is actually not the molecule which is proton sponge. There are some other groups, nitro groups are there, but this is a template, okay? And these kind of molecules are called proton sponge. So I actually would tell about proton sponge. And in actual proton sponge, there is so the proton sponge molecule is actually the nitrogen contains ethyl groups. Okay, nitrogen contains ethyl groups, not methyl, but this is a template. So when we compare the acidity, this C will be most acidic, right? Sorry, C will be most basic, right? So C is most basic. Then between A and B, it should be B. So you are also thinking that inductive effect is present in A. Yes, maybe because we cannot see any other effect. Okay, I will try to confirm it and I will let you know. But for now, we can consider that C is most. Yes, yes, yeah, because here only hydrogen atom is there, so steric inhibition is not present. Yes. So from both sides they are pushing. So that means the delocalization is not that much high, right? And also another thing is here you can have a rotation, right? You can rotate. You can have rotation around this bond, which is not there here. Okay. Yes. So if we now consider rotation, then the order will be different, right? Because here both are donating inside the ring, so their mutual effect will cancel, and the nitrogen lone pair will be mostly available on the nitrogen atom rather than inside the ring, right? But because here you have a rotation, and when the two rings become perpendicular to one another, then what will happen? Both can now donate inside the ring, right? Right? So that means the basicity of B will then decrease. Okay, so we are not sure about this order, but C is a proton sponge and it is highly basic. That is for sure. About A and B, there is a confusion, and I will clear it in the next lecture. Okay. Yeah, in this lecture itself, I will give the example. Okay, so then this one A, B, C, and D. What will be the order? Can you tell? Hello. So this system actually resembles this one, right? So here, so I have to erase it. There are a lot of things. I have to erase something. Yeah. Yeah. So this is A, this is B, this is C. Can you tell again? C, B, A, and D. Yeah. So C is most basic. There is no confusion, and D is least basic. There is also no confusion. But can you explain why you think B is more basic than A? Yes, so it can come this side as well as this side, right? But here it can only come this side. So everyone understand that? Okay. So this is the order. Now another one. Another one. I have to again erase it. Uh, yeah. So this is the thing. This is A, this is B, this is C. So can you tell the basicity order? Sorry, here actually it is acid. It is talking about the acidic nature. So this proton and this proton and this proton. These are the acidic protons. So can you predict the acidity order of these three? Yes, tell. B is most acidic. Then okay, C is least. You are saying so. So you are telling that B, then A, then C. Why? Yeah, same is for C also. C is also carrying a positive charge. It will form a carbene. It will form a carbene here, but that is neutral. You understand? It will form. Hmm. Yes. So again, we have to look first into the first point. Then so we have to follow the hierarchy. First, we have to look into the bond strength, then electronegativity, and then the stability, right? So it is CH bond. CH bond means C is always less electronegative than nitrogen, right? So that means A and B will always be more acidic than C. So C is least acidic. Now between A and B, one is positive species which will become neutral, and another one is neutral which will become negative. So that means B is more acidic. Clear? Understand? Okay. Now here nothing to say more here actually. This one, this one, yeah, yeah. So B is most acidic, then A, then C, because C is least acidic. We understand because it is CH bond, and in this cases they are NH bond, right? So see now between A and B, you can see this is a positive species which will become neutral when it will lose a proton, right? And this one is already a neutral species, so it will acquire a negative charge when it will lose a proton. So which one is easy, taking proton from a positive center or taking proton from a neutral center? Yeah, so that's why B is more acidic than A than C. Understand? Okay. So then steric effect, so I we already discussed about it, the steric inhibition of resonance. Yeah, tell. Nitrogen, what nitrogen in, what is that? What is that? Which one? This one? This one? This one you are talking about? This one? Yeah. No, in B and C, in both cases there is no inversion because they are rigid system. See this is tied. This nitrogen is tied with this bond, so there is no inversion. In both B and C, there is no inversion. Now, because in B there are two carbon atoms here, and in sorry, in C there are two carbon atoms. In B there is only one carbon atom. So B is more rigid. C is more flexible because two carbons are there inside the ring. Can you see that? See here you have two carbon atoms, right? So it is more flexible, and this one is more rigid. This one is more rigid. In both cases, inversion is not possible because it is a tricyclic system. Inversion is not possible. Okay. Yeah. So now steric effect. So this is the case of steric inhibition of resonance. For this, the steric inhibition of resonance is not present. At the same time, uh, it will form a hydrogen bond. It will form a hydrogen bond, and the system is completely planar. It is completely planar. Yeah, so like this. So it will drag its all electron inside the ring, and also inside the nitro group, right? So because of this planar situation, there is no electron available on the nitrogen atom at all. Its basicity drop down very much. Whereas for this one, you can see for this one, because you have methyl group present, so it will create a steric hindrance, and now the nitrogen lone pair is actually perpendicular with respect to the ring. Sorry, not like this. uh, I have to erase it. Yeah, so here you have this, sorry, yeah,